Okay, let's start. I'm actually on time today. So today we're going to continue talking about the bits of the address space, and specifically we wanted to talk about. I wanted to talk about something what is called a buffer cache or a page cache in Linux, right? It's essentially the subsystem which allows caching almost everything in between the disk and the memory, right? So it's kind of like almost the last part of this virtual memory organization series, after which you can essentially, after which you should have a decent understanding of how it works in Linux. Okay, so just a quick recap. So remember we talked about, oh, this one is here. Why is it here? It should move somewhere. Can I even grab it? Oh, I cannot. Okay, let it stay there. Not sure why my video is there. Not sure. But okay, so just reminder, remember, this is what we were talking about for the last couple of times, right? So each process in the system is represented with a task struct. Task struct has a pointer to the memory map, right? So mmstruct. mmstruct itself contains a list of virtual memory areas, those square boxes, right? Virtual VM area struct. They are also maintained as a red black tree, so the system can quickly look up from the address into the virtual memory area and then go into and do something. This one? No, not mine. Something. And what's happening here is that like there are multiple kinds of regions in the address space, right? So for example, here, a typical process, again, same kind of representation. So task struct of this binary program has a memory struct, contains a list of virtual memory areas. Each memory area represents a region in the virtual address space, which is here, right? So for example, this one is readable and executable. It's a text section of a program. It's backed up by a file. And remember that this VM area struct allows you to like descend into a file data structure, right? Similarly, another virtual memory area is here. The difference is that this is not executable but writable. It's a data part of the file, right? But essentially goes back into the same file. BSS, another area, readable, writable. Remember, it's not kept on disk. So there is in L file, there is just a header which says, okay, allocate certain amount of space in the address space. And this is what the operating system did here, right? Then another virtual memory area, which represents a heap, for example, right? And some memory mapped files. So for example, here it's a library, libc, again, virtual memory area, readable, executable, because typically you don't have to, I mean, it's a position independent code. The same file can be shared between multiple address spaces, right? And so that's why it's read-only and executable. The next, like the linker itself, ld.so, is also another shared memory library. Again, they just occupy adjacent regions of virtual memory here. And then on top of that, we can see a stack, for example. It's readable, writable, and grows down, meaning that remember that if you have a page fault outside of the stack, but it's this virtual memory area is expandable, instead of like reporting a stack fault, it will add additional page extending the stack, right? So remember from previous time. So again, just making sure that we remember what was happening, right? Okay, cool. So, however, in all these systems, and we'll start with x86 just to remind what's going on there, and specifically in Linux, all of it or most of it can be actually taken to disk, right? So any of this parts of this regions, and I mean, specifically, let's imagine there's a page here, right? And it's actually backed up by a physical page somewhere else. This page can be taken to disk, right? Into a swapping area. Or for example, if it's a read-only file, you don't even have to take it to disk. You just throw it away saying, okay, if anything, I can read it back from file again. So we don't really have to maintain this read-only copy anywhere in the swap area, right? And essentially, everything, every access to a file will be buffered with something what is called a buffer cache, or in Linux, a more generic cache, which is called a page cache. I will explain how it works, right? But the high level overview is that the idea is that we're gonna cache accesses for subsequent accesses, right? So presumably that will allow us to hit the same like block or allocation of in a file multiple times, and essentially in a manner that is completely transparent to the applications, right? And in Linux, as I was saying, all requests go through a cache. So for example, if you have user tries to read something from a file, the system will first check that the like part of the file is already in a cache. And if not, since the Linux cache operates in units of pages, the new page will be allocated and added to the page cache, and then the data will be read from disk, and it will be kept in that cache until it's evicted, right? And it's not uncommon in Linux that all the memory is occupied by the page cache. So essentially, if you Linux essentially like never kicks out the pages out of the page cache unless it needs more space, right? So don't get surprised that all the memory in Linux is allocated, right? But this is with the expectation that you have a chance of hitting the same caches again, right? And for the write cache, for the write access, the logic, high-level logic is the same. So if the page is in the cache, if not, essentially allocate a new page, fill the data from disk, and then do the write. And in fact, the Linux will not immediately flush the write back to the disk, right? But we'll keep it around, hoping that you will do another write, and this will allow Linux to prevent to combine multiple disk writes into a single disk write. But of course, at the price that if you lose power at this point, you will lose this data, right? So sometimes you have to do something like an fsync to make sure that, or flush, make sure that all data from the cache are actually hitting the disk. Okay, so the high-level motivation is clear, right? So we're going to build this buffer cache. The way I will like talk about it, I will first quickly recap the buffer cache, organization of the buffer cache in x86. So does anyone remember how it worked? x86 had a relatively simple, or actually very simple buffer cache. But the similar buffer cache existed in Linux up until like kernel version 2.4, I would say.
I remember something when we keep a file system device for final stuff, we will write this kind of cache instead.
No, correct. Like in remember in x86, when you do a read, for example, and you say a file descriptor, let's say a buffer, which points to a user memory and a size type of length. From a file descriptor, remember that there will be a table associated with each process, table of file descriptors. From this number, you will go into a data structure, which is called a file. From that file, you will go, because the file can be like that. It can be, for example, I think in x86 it can be the pipe, right? But if it's really in disk, you will have an inode, right? And at some point, in order to do a write, you will follow this chain, and then you will use those methods like bget, forget how the write works, bwrite probably, and something called the brelease, right? And the data structure, do you remember? I mean, imagine if this is your disk space, right? Starting from block number 0, then 1, and so on. This is on disk. Imagine you're writing something in a file, and maybe the location of this, the actual data, like there is a file, right? Maybe its position actually 0, but physically it's located in the block number, let's say 255 on this. How do we implement the caching architecture, or how does x86 implement this caching architecture to make sure that if you're doing multiple writes or you do a read and then a write, you hit something in memory first and then what is eventually flushed to disk. What was the organization? Do you guys remember? Well, transactions. Let's suggest a data structure first before we dive into synchronization and transactions. Well, imagine like, again, this is a homework assignment or a job interview, and someone asks you to invent something what sits in between here. Do you remember how X6 is doing it? Probably not before because I never assigned a homework, but let's quickly design our own because I think it will help us to understand how to design it better.
So I was the question, exact question.
The question is like, when you do a read and write, design some data structure here, which allows you to read this guy once in some data structure in memory. And then maybe do multiple writes or multiple reads feeding this location in memory, but not going to disk. Just because a trip to a disk is, let's say, 10 million cycles. And a trip to NVMe, maybe 10,000 cycles or 20,000 cycles, right? So the NVMe is faster, but still a lot, right? So what would be this data structure, which we will call a buffer cache, which everyone calls a buffer cache? Will be a log. Okay, yeah, let's first design it and then figure out synchronization. So how can we build it? Anyone?
Please put the inode number.
Say again?
We need to put the inode number. In the past, in the past page, if there is an inode is popped up like in the past paper, then we will get this in the cache property. So the field this is an array of like latest inodes.
Okay. Like, let me decipher what you say, although it's a little bit not clear, but you say we will introduce an array and we'll call it a cache. And in this elements of this array, what you are suggesting, we're going to keep something related to inode, but I suggest we keep something related to blocks from the disk. And essentially we can address them by disk block numbers, right? Why not? Because inodes, I mean, let me refresh you. So how the organization of a file system in x86, which is representative, right? So beginning of the disk, let's say block 0 is called a super block. Super contains metadata about several areas on disk. One is, for example, inode array. One is maybe a bitmap of allocated and unallocated blocks, right? In the disk area, another area will be called a log or a journal to implement the transaction. But this data area is essentially represented by those bits. If this one is 1, then this block is, for example, already allocated, right? And then inodes are simply, each one has a number. Let's say this one is number 0, this one is number 1. And then the convention can be that either in the super block, you say which one is the root inode, or you can say inode 0 is the root inode, like whatever you want, probably more flexible convention. And this inode itself, it says, look, I will maintain, like if we zoom in into this inode, it will be an element with some metadata, but what's important, it will have some number, I think in x86 it's 12 entries, which map from, it's a mapping from block number. So just switch it off. It's a mapping from a block number to from a logical, like inode represents a file on disk, right? Virtual address space kind of. It says block 0 will sit in the data block 55. So then this entry will be 55, like for block 0. For block 1, imagine this entry will be sitting in a block, let's say 13 right? It's not date and 13, it's just the disk for disk area 13, so you will put 13. And then if you run out of those 12 entries, this entry will point you to an entry in the data area, for example, this one, which will contain like recursively lookup, right? So do we remember this? inodes on disk, right? And inodes, I think I forgot exactly how you allocate an inode in a file system in x86. I think you literally will be doing like a linear scan to figure out which one is still available. Then you'll get a new inode. And if you want to represent a root directory, this inode, let's say 0, will be always like it will be just a regular kind of like an inode file, but it will contain a table internally which will map file names like bin to inode numbers like 13, which represents the directory bin, or a file foo, which inode represents like 7, for example, right? So this is a directory inode, the entry or whatever it's called. Right? Remember this trick? So everyone is good on the file systems now? Any questions about it? Quick refresher, right? So obviously, when we somehow open the file, when we did open, and we pass the human readable name like /bin/ls, for example, for whatever reason, maybe you wanted to read or write ls, it will first go to the root inode, or like there was a service which translates those strings to inodes by splitting those substrings called namei from name to an inode. And then if you actually like follow these directory entries recursively, there will be an entry bin. It will open inode 13 here from disk. We'll read it. It will also contain a table, and one entry in the table will be, let's say, ls, and that will be inode number, let's say 17, and then it will read 17. Oh, sorry, not from the bit, but from the inode area, right? And then open 17 returns you allocates a inode in memory, gives you a file, figures out an empty entry in a file descriptor table, and returns you, let's say in this case, number 3, file descriptor number 3, right? Good. This is, everyone is clear on that, right? So obviously, when you do a read, your operation will go back to the inode, and at this point, inode will represent a logical space of a file, similar to how I did it here, right? So inode says, okay, I start from address 0, go to some max address, and imagine you didn't do any 6 or anything, so you're just reading from the beginning. And imagine you're reading, like, let's say, 200, 2000, whatever. What's the good number? 512, 1024 bytes. And since the file system says, okay, you're really reading 2 blocks underneath because the blocks are 512, it will say, look, I will look up in your direct entries where these blocks are located on disk. And it will be like block 77 and 18, for example. And then it will have to go and read 18 and whatever, 77 from disk, right? So at this point, it means that probably those 18 and 77 have to be kept in this array, which you suggested, right? It's nothing to do with an inode. So you can probably have some kind of an inode cache on the side, because you say, what if I frequently accessing this area of the disk? It's also a disk block. It's maybe disk block number 1. But again, maybe depending on how your API works, you can put this block number 1 into this cache as well and say, I'm caching number 1. Right? So this is called a buffer cache. So, okay, so help me with the organization of this buffer cache. How is that supposed to work? What do you think? Like, we already know the layout of the file system, kind of everything is in front of you. What's the caching procedure? What are we doing when we're trying to bring a block from disk into the cache?
Mapping the 0 to 255.
Wow, hold on. You said that this is an array. Immediately you face a problem of managing resources of this array. So you kind of need an allocator on top of this array, saying that which entries in this array are free and which are available for caching, right? So how do we do this?
Is the tag free or not? or like.
Well, you're saying I will maintain a bitmap. That's one option.
Yeah, you know.
Now, again, don't suggest bitmap on job interviews. Suggest something better. So what's better than bitmap? We've seen a lot of it. Linked list, exactly. So instead of a bitmap, we can either say, look, like part of this array has metadata, and this will contain an element to next, for example, right? And the other part will be data, right? Why not? And if it's a linked list, you can, in fact, maintain not just like free and available elements, but also you can maintain an order of accesses, and you can track the least recently used access, right? Which means that if it's at the very end of this list, you can say, wow, maybe it's time for you to go out because you wasn't accessed for a while. X26 actually kind of mixes these two, and they actually, X26 itself maintains a flag kind of like free and or not free. So X26 does not maintain two different lists of free and non-free elements. And they actually scan the entire list trying to find a free one, which essentially introduces a linear complexity, which is not good, obviously, right? And that's why the buffer cache in X26 is not ideal. But we can probably, since we know how to build allocators now, we say, look, by the way, well, maybe it's two lists or something like that, and there will be a separate list of free elements and non-free elements, right? Although, on the other hand, you can counter argue and say, look, since it's a buffer cache, there should be no free elements, right? We only need to know which element to kick out, right? Because what's the point of maintaining empty elements, right? So we ideally should keep it always full, and then when we need a new one, kick out the one which was not used for the longest amount of time, right? Agree? Okay, so, and that's essentially what X26 is doing, right? Do we remember or not? So buffer cache was sitting at the very bottom of the X26 hierarchy to go synchronizing accesses, because it was also kind of like introducing locks on those elements of the list, saying that maybe someone is reading them, so no one else will be able to read at any given point of time. And what is happening here is that, so here we had just quickly highlight this. So what we have here is, this is the buffer cache itself. That's your array of buffers, and each buffer has some metadata itself, which we're drawing right here on the top, and the data array here, which is 512 bytes of cacheable block space. And this pref and next pointers maintain the LRU cache, and it has information about if it's caching some block from disk, it will contain the block number, device, because maybe we have multiple disks, and flags kind of like busy, valid, whether the data from disk was already read, or dirty, meaning that it was updated and it has to be flashed back to disk, right? Agree? And X26, the algorithm in X26 was relatively straightforward. So it was providing those, the interface of block read, block write, and a block release, essentially, which allows you to say like the block is available for the next user. So this read and write, we're implementing synchronization, right? And the algorithm was something like this is an example usage. So for example, here, the file system, which implements a transaction, which you mentioned, says, okay, I will read a block with a specific number, read another block. So this is a left, this is the logging block, and this is a data block. To read two of them, so these hit the buffer cache, and eventually maybe like blocks are actually read from this into the buffer cache, but then it returns a pointer to the buffer cache. And then what it does is uses mem_move to copy data from here to here, from one block to another. Then this one is written back to disk because this one was dirty, and both of them are released, meaning that, you know, if someone else wants to read or write into this block, then the write is allowed. So the next thread or process in X26 can acquire ownership of this block. So one interesting detail here is this: when you do a beget or block read, at this point, I think locking is happening. So you are I mean, there are multiple ways to implement locking, but specifically the high-level idea is to prevent from two processes from writing into the same block at the same time. Again, you can argue whether it's a very useful policy, but okay, it's useful probably, but you could probably argue that okay, maybe we can come up with different synchronization policies, but this is what Exo 6 was doing, right? And specifically what when it was trying to implement this eRead method, right? So what was happening internally, it has a beget method, right? And in the end, it will figure out a free block or a block in a buffer cache. It will check whether it's a block in a valid state, meaning that it was just recently read from disk. If not, it will go to the IDE, which is a disk drive, and do a read-write operation on it, and then return it to the reader, right? But if it's already was in a devalid state, it was just, maybe it was cache from previous access, right? It will just immediately return. And this internally, this beget is implemented in a very kind of naive way or coarse-grained way. So it acquires a global lock, meaning that no other part of the system will be trying to even search in a buffer cache, right? So it's one global lock, then it traverses the linked list, right? Starting from the head, hoping that this least recently used policy kicks in and the recently used elements are promoted to the front of the linked list, right? Meaning that you might amortize those searches instead of doing ON, maybe do something smaller complexity, but lower complexity, but I'm not exactly sure how the numbers work theoretically, right? And what it does, it essentially says, okay, I'm looking for a block belonging to a specific device and with specific block number. And if I can find it, so device matches and the block number matches, I will check for the flags. And if it's not busy, I will set the flag to busy and will release the buffer cache. At this point, it releases the global lock, but sets the busy flag in the metadata in the entry, right? Which means that the next, whoever wants to acquire it, if it sees busy, then it will go to sleep here, right? And we'll be waiting for someone to release this block. And if everything is successful, meaning if it's a hit in a cache, then the function returns. If, however, it's a miss, it will continue and logically will try to say, okay, I will try to pick up a block which I can throw away from a buffer cache and use it instead. So it will again do the search, which is again not super ideal. It says, okay, I'm looking for a block which is not busy and which is not dirty, right? And if I find this one, right, meaning it's not dirty, it was not modified, so it was already flushed to disk, I will reassign it to this specific device and a specific block number, will set flag to busy, and will release the global bcache block, right? If somehow it cannot find a block like that, it can panic, which is also not an ideal thing. Okay, so we got this kind of intuitive or like first level approximation of how we can implement this data structure based on Exo 6. Now let's discuss a little bit. So what is wrong? What is not ideal about this data structure? Okay, yeah, so linear search, not ideal. What else? We have a big lock. Yeah, exactly, big lock. So very coarse synchronization discipline, meaning that only one process in a system can perform not even a read. Okay, maybe like they can overlap the reads, but cannot access the buffer cache, right? Mm-hmm. Coarse lock. What else? I actually was in a position of porting this code. We once were building a database which was running inside SGX. SGX is this secure enclave, and I needed a buffer cache for this SGX thing because my database buddies, they were implementing some very fancy buffering, algorithmic buffering technique. And I said, okay, let's just build a buffer cache and it will all be much easier. However, and I took this code, right, and I ported it inside SGX. But I mean, I was penalized obviously immediately with this linear search course lock. And of course, I didn't like this panic, right? So that kind of sucks at this point. So for whatever reason, x86 does not try to aggressively. So here, the search condition here is that it's not busy and it's not dirty. Although theoretically, you can just say, okay, I don't care if you're dirty. I just don't want you to be busy. If you're not busy but dirty, I will just flush you to disk forcibly, and then allocate this block. So this change can be done as well. Okay, but okay. So now the question is: imagine you are a Linux designer and you want to build a better buffer cache. So how can we go about it? And again, I was also in a position like that a couple of maybe a year ago. Jafank was on board as well. So we were building a new operating system. We got stuck with the buffer cache. So can we improve, and how? And then I will tell you how Linux improves. How can we? Okay, these two things are most interesting. Course lock and linear search. How can we address these two?
With a tree structure to decrease the search time capacity.
With the tree structure. Okay, that's a good idea. So how can we do it? What kind of tree structure we can implement? It's a little involved, I would say, but let's try it.
Balance.
Well, we can say, let's have a tree, but what will be the input to the search? What are we searching for? Like I can scroll here. So this condition is more explicit here.
Device block number.
Yeah, so we need to let's say block number for simplicity is an input, and then maybe blocks are somehow balanced with a tree. And at the end, we can either say, yes, there is a element found, or if it's not found and it's null, then we say, no, there is no such element, but okay, we are avoiding this linear scan already, right? So that seems logical, right? And maybe we can also maintain those elements in a doubly linked list. On a doubly linked list, recently used a list, meaning that sometimes when we want to kick something out, instead of like searching through the tree, we say, look, by the way, we know the head of this list and went to the tail, and we'll just like kick something out from the tail, right? Because that's the oldest block, then we will remove it from the tree, for example, this one goes, right? Make sense? Right? Everyone agrees? I mean, what kind of tree, let's say, again, the one which I mentioned, red, black, but any kind of tree will do it for us, right? At this point. Okay, cool. So we address the search. And maybe, remember, I kicked out the def, so maybe each def will have its own tree, right? Why not? It seems to simplify things because we don't have to maintain block numbers for different devices in the same tree, right? Kind of logical. How can we go about the coarse grain locking? So the big lock which we're acquiring here.
That the log would be combined to the tree, like we can synchronize by branch.
Like implement locking within the tree?
Yeah.
Okay, that's doable. But no, and in fact, it's okay probably, right? I don't know how to build this tree myself, but I'm happy that someone else will build it for me. This tree with finder and locking, they do exist, right? But tricky, because especially if you want to rebalance, then the locking becomes tricky, but you can do it, right? But what about this kind of idea which Linux kind of goes after And they say that instead of maintaining a single buffer cache for the entire system, they will maintain a buffer cache per file. Why not this, for example? Then you say my lock will be like around this access to the file, or even like if you're super smart, you can do fine grained access within the tree. But it kind of allows you to say, look, why do we have to mix everything together in a single buffer cache? If all the accesses kind of go through the file, then it seems to be logical to attach a buffer cache to a file, right? Per file. And somehow, I don't think when we were designing this last project with Jafang and Zandong, and Jerry probably was not on board there, then we kind of didn't try this idea for whatever reason.
If you set every private buffer cache for each file, but you still need an overview like the data, that will still use the.
Like for example, for which operation?
For example, you limit the number of the buffer cache. You said you have millions of files. So your number of buffer cache is limited, so you need to maintain this kind of global information. So you still need a big.
Okay, great comment. Okay, let's see how Linux does it. So they say, what does this mean? You say, why not to make it as flexible as possible? And instead of like reallocating anything like x86 does and this buffer cache, there was a number, right? So for example, here they said there is a size of a buffer cache, B size, right? Oh no, sorry, this one, nbuff, number of buffers, nbuffs. What if instead of doing this, we will devise a dynamic allocation scheme? Meaning, if we need more space for the data entries, we can allocate them dynamically. Why not? We already know how to build an allocator, right? It seems that this generic allocator can provide us memory when we need. We open more files. We allocate more memory from the allocator, right? Place these elements here. And then the only thing which we need to do, like you say, the global view is when you start detecting stale entries, right? So maybe one way is to connect them all in one global list, but that doesn't work. Like, because obviously you promote, I mean, you can do probably different tricks, but yes, you need this global view of what was accessed recently, or maybe you can recompute a similar statistics by, if you maintain a list of files in the system or something, then you just somehow say, I will lazily go through this list, detect the not used entries. And remember, we have this reverse mapping data structure, which I talked about a couple of days ago, which says, okay, if this entry is an entry in a file, I can then go to all the address spaces which map this entry, right? And I will unmap all the page table entries and make sure that I can actually take this thing back to disk, right? Agree? Does it still make sense? Or is it too complicated at this point? Right? Okay. And this is roughly what Linux is doing, right? So they say, look, a buffer cache per file, dynamic allocation of memory, and actually in the unit of pages. So they say, okay, forget about blocks. We used to have blocks, that's fine. But since we manage memory in the units of pages, like for example, if you want to take the whole page down and map it from everywhere, then like make sure that some consecutive regionals of disk are kept in this page, right? And we either take the entire thing, and then if you have a page fault, then the whole thing kicks in. Remember, you go from a page to a virtual memory area, from virtual memory area to a file, from a file to something what is called an address space, and you read it back. Question? Can you use a hash table like thing?
Because say we use like the unit number and the say block now, so combine them for the like key. Yeah, there might be some relation obviously.
You probably can. So, and that's a great question. Like, I will not be surprised if some buffer cache implementations, and especially research ones, attempted this approach because it seems logical, right? I didn't follow. What we can do is that my plan was kind of like go through Linux fast to give you just some kind of a general overview of what's going on, and then go into the research approaches. I was mostly trying to go into something like virtualization, fast device drivers, but we can also take a look at attempts to build fast buffer caches. And I myself, I'm interested. I didn't read the literature at that point, so I don't really know what's going on. Like just anecdotal evidence, one of your former classmates, Cody, who was a student here, then he went to MIT because he was an undergrad here, then he joined for a PhD at MIT. We were friends when we were students. He built a fast buffer cache for an operating system, which he developed in a language which is called Go. Right? I'm not a big fan of this project because Go is a garbage collected language, so not clear what was the reason, but they were trying to explore the limits of pushing garbage collected languages into the systems area, right? And one of the side contribution of the paper is a faster buffer cache, but I'm not entirely sure whether it's like research fast or just like as a byproduct of this Go and some. Like what I mean is that I'm pretty sure there are multiple attempts to build buffer caches because it seems like a research problem. Because again, your main concern is to avoid locking because that stalls the entire system. So this moves the lock from the entire like global buffer cache to per file access, but maybe it's still not granular enough. And in a cache table, maybe it's possible to build a log-free hash table. It's possible to build log-free trees, but it's hard, easy to make mistakes. Hash tables are slightly easier, but so probably it's doable, I would say. Yeah.
So is the LR do exist per file?
Great question. I don't know, Stefan. So like in my next homework assignment, which will be explaining the organization of a buffer cache, you guys will have to explore and tell me. I don't know. I quickly read and I'm not sure. I don't know. Because I think both organizations are possible. I don't know which they chose. They probably had a trade-off to solve. But okay, so let's take a quick look at how Linux does it. Any other questions about the approach? I was actually kind of surprised because I didn't expect them to do a per file, and maybe I misunderstood it, but that's what I understand, or at least. Okay, cool. So x86 is here. So then now buffer cache in Linux. So again, the most central to this organization is this data structure, which is called an address space. We kind of mention it in passing, and maybe as you're writing, you hit it again. But just to remind that this is where it is. So it sits here, right? An address space. It has a collection of address space operations, right? Which allow you to read and write from disk, right? But it also will have something what is called a radix tree. Do you remember what radix tree is? It's kind of like a page table. So it's not balanced, but kind of good enough for them, right? And the general kind of dependencies, remember, so we have processes like task struct. Task struct has a pointer to memory map struct, and then it will have a list of virtual memory areas, which I had in a previous slide. And then virtual memory area will have a pointer to a file. The file will have a pointer to directory entry, the entry, and then the entry will have a pointer to an inode. An inode will have a pointer, this I_mapping, and this one will lead us to an address space. So, which means that, okay, let me quickly explain. So for example, when you do like a read, you hit a file, and then you descend into an address space. From an address space, you will look up in this radix tree, and the radix tree will have a pointer to a page pop, pop, pop. And I think the entry here will be an offset within a file, which means that when you land on a page, you already know, like, if you have a file and you say, I read the specific byte, you round it down to a page, or to a block, and then you round it down blocks to a page. Page will be here, right? And essentially you say, look, I will just read this data. If the radix tree says no, then you use this address space operations to first, like, you allocate the new entry, new page from the buffer, from the body allocator, for example, add it to the radix tree and read the data from disk into that page, right? So that's one way if you do like a read or write, or if you, for example, if this page is no longer in a buffer cache, so it was swapped out, remember you have a page fault, you remember this idea, I don't know if I have it here on the slides, that we can go you have a tree here, a red-black tree, right? Remember this thing? So red-black tree allows you to look up a memory area. Within the memory area, you descend those pointers, get to the address space. And if it's backed by a file, you search the radix tree, figure out whether the page is in the buffer cache. And if yes, just maybe it was just unmapped and you remap it back, for example, stuff like that, right? Does this make sense? Is this clear? I'll go a little forward with this, but just wanted to make sure that I stopped for a second. So it's kind of like, it's kind of clever. So it kind of binds into their organization of virtual memory, right? So essentially you say, look, my cache is now maintained at the units of these address spaces, and address spaces are attached to files, right? But I have a connection between the virtual memory area, right? So which we've seen here. I just wanted to go back here again, a connection between the virtual memory area to a file, right? And so if you have a page fault, right? So you first go into the struct, use this red-black tree to locate the VMA, right? This is the entry here. One entry of this red-black tree is a VMA. From this VMA, you essentially go down to a inode, then to an address space, look up this radix tree here, and essentially check if the page is present. Does it make sense? Okay, so then a couple of other so that's probably I already talked about this radix tree. More specifically, the way it works in Linux is that, again, so the address space has a pointer to the radix tree. So radix tree is exactly the way to think about it is to, in Linux, it can be variable size, kind of like the page tables of with pages of different size, right? But the size or the depth of the tree is maintained in the metadata, and then it triggers the interpretation algorithm. So, for example, in this example, I show it's from the book, two radix trees, right? And the height of one of them is 1, and the other one has height of 2, which means that the radix here is 64 from 0 to 63, right? So for example, if you have an address which you want to translate, if you have 64 entries, then the lowest 6 bits, one of these bits will define the entry in the radix tree, right? If your height is 2, then it's 60, then it's 6 by 2, then it's 12, and the lowest 12 addresses will decide the translation. The upper 6 will choose an element here in this level of the tree, you descend down, and the lower 6 will choose the entry in the nested level of a tree, right? Make sense?
What's the count mean?
What's the what?
Count.
Count?
What does it mean?
I think it means that this radix tree has 2 slots active, but I don't remember how it's used. The reason that it's variable height is that it dynamically because it doesn't really know what is the file size you're going to be servicing, right? And initially, optimistically, I don't know what number it allocates, but let's assume it allocates the height 1 for a very small file, right? And you say, look, it's sufficient, lookup is fast. But then if you suddenly issue an address which is like higher or outside of the range, then you have to restructure the tree, which doesn't break correctness, just slows you down with a lookup, right? Because the constant for this log-n lookup will be higher, right? Make sense? Okay, so that's pretty cute. So that's one way to maintain files of different size, right? And you can quickly count up how much, which height of the tree covers which size of a file. You can quickly go to terabytes, I think, without like much overhead. So that's nice. So we understand how it works, and the radix tree lookup essentially, just as you say, I already had it like it encodes which bits. So very much similar to page tables. If you understand how the page table lookup is always fixed by the hardware, and you start you say it's not like you say, well, I will first check the depths of the page table. It's always either the level is fixed, and let's say 5 to 4, and then you go down like with 9 bits, because 9 bits is encodes what is it, like 512 entries, right? That's how many entries fit in one 4K page, right? So 512 entries here, and then you will use this 10 bits to look up the topmost level of the page table, then pick an entry here, go to the level below, then use this 9 bits here. And the way the hardware is organized, it can say, well, it's actually a super page. So you don't have to use all the rest of it is all set within one giant, for example, like a 2 megabyte or a 1 gigabyte page, for example, on 64 machines, right? Okay, cool. So we understand that. Linux, however, there was another interesting observation here, which I kind of like glanced over, that if x86 was managing memory for the buffer cache in terms of disk blocks, which is natural because you say, okay, read and write files in the units of blocks. Actually, Linux says, okay, forget about it. We will manage memory in the units of pages. And if multiple blocks fall into a single page, we'll read multiple blocks from disk and bring them to memory and put them into that page. In most normal cases, those blocks will be consecutive because it simplifies management and everything, right? But that's kind of nice because it kind of hits the middle ground between the page management and the disk management. And also, like, it also allows them to the page cache is not strictly geared towards disks or files, right? It can be also anonymous memory. And for example, anonymous memory, meaning that it's a heap not backed up by a file, and maybe it's actually on a swap device or something like that. But they can also like use those tricks and make sure that they they can also cache those entries. So for example, maybe something like if you're mapping, and I'm like not 100% sure, but if you, for example, have a virtual memory area which leads to libc, and you never really like access the libc yet, so because you didn't start executing yet, you hit a page fault. The question is like, where does this page is coming from? It will be in a buffer cache, most likely, right? And then like the same infrastructure can be used for, I got back to a file, obviously, right? But imagine it's some kind of anonymous memory which is shared between multiple processes, right? For example, we establish the region version, and then in one process it's already in a map, and another one still, or maybe it was in multiple still in a buffer cache because the daemon which scans the candidates for the swapping, which is called pdflash, you can get to it or something, right? So you can reuse the same mechanism to essentially provide caching of memory as well. And it's kind of an elegant solution, I believe. Instead of like decoupling the buffer cache and the page cache, you just manage them as one single uniform data structure, right? So that's kind of cute, I think. So again, so maybe the next time we'll be building an operating system, we'll try to adopt a similar approach, right? However, Linux being Linux, obviously, they said, okay, that's all good, we'll have pages, but then they also have an alternative, the true buffer cache deal mechanism, which is very much like x86 buffer cache, which is block-based, which is a little, I mean, I don't know exactly how it works because I didn't dive into the details, but at a high level, they say, look, in some cases, we want to bypass this page level mechanism and really want to read a block from a disk, right? And we want a buffer cache, which is similar to x86, right? So what they have here is they have a collection of data structures that allow them to essentially kind of like similar to our x86 story, essentially allocate a page of memory and then have multiple data entries. So let's say here in this example, 4 blocks cached within one page, but they don't have to be consecutive. And they have like a search algorithm which uses external memory, which essentially maintains the metadata about those guys as a linked list. And I don't exactly know how the search works, but my guess is actually it's again linear scan, very similar to x86. And they bet on the fact that the list recently used policy will promote the frequently used elements to the front of the list. So they will be, the accesses will be amortized. But you will be, I mean, I was surprised again that they still, I mean, I don't know if it exists in like most recent version 6, but at least in this, the version which is covered by the book, like version 2.6, this mechanism still was there, right? Just be aware that it can happen that, you know, you will see the data structures and you don't get confused, right? So they somehow have both, like both the page-based and this the block-based hierarchy, and it's fine. So probably again, no one else would think of implementing it, but Linux being Linux did it, right? And then in a typical scenario, when the page contains consecutive blocks, you will, like, your search algorithm will be essentially taking a block number. You have to convert from a block number to a page, right? Because your Redis tree maintains pages. So since each page contains n blocks and you know this, so the conversion is trivial. So you just divide the block number by n. And essentially, if you like the page private field will contain a pointer. So page private will contain a pointer to the buffer head. Sorry, to this one. Right. Okay, so I guess this is actually it. So I don't, my story about the buffer cache is done. So just a couple of things, right? So I signed one homework, right? So this is due, I think, Wednesday. So I will try to assign a homework, which is actual kind of lab. So remember, the lab is actual programming assignment, which is to build body and slab memory allocators for x86. So my office hours, then let's do an hour before the class on Wednesday, but feel free to shoot me an email. And if I'm around, feel free to stop to talk to me if you need. But Piazza is there as well. So we have Piazza connected from Canvas. I don't know how many people sign up. We will set up the website as well, probably, hopefully tomorrow. So any questions? So do we understand how to build? You guys, you were a little fuzzy about the buffer cache in x86. So I'm a little, how is the whole x86 story going? We'll see by trial and error. Okay, so then good luck. So then I will assign this lab assignment, and as soon as I can, we'll see what our next, probably the next writing assignment will be about the buffer cache. But buffer cache is a lot simpler than the entire virtual memory subsystem, but still like a little bit more involved. And then we are close to being done with the Linux virtual memory management. So good. Then I'm done. Thank you so much. See you Wednesday.